Good evening, ladies and gentlemen. Welcome to Newcombe and Midlands, to the last lecture of the season. We are pleased this evening to have Nigel Jopson to talk to us. He is a biochemist by training and has worked in the paper industry for many, many years. He worked for PIRA, the Paper and Packaging Industry Research Association, as a consultant for a long time. He gave us a talk about 3 years ago on paper manufacture, including video clips of making sheets of paper and so on. And he's come back today to give us a talk called Boxing Clever, a brief history of corrugated containers, which I think they're very ubiquitous item now, with particularly with all the mail order that goes on now, particularly with people not wanted to go to shops and things. So we're all very familiar with them, but their technology and so on is probably not very well known to us. So please tell us all about them.
Thank you, Phil. Well, good evening, ladies and gentlemen. The title is Boxing Clever. And the reason for giving this talk is that corrugated containers, and not cardboard boxes, are conspicuous by their ubiquity, but very few people give them a second thought or a further glance. So what I'm going to talk about tonight is to define what corrugated board is, its engineered properties, how it's put together, why it's put together, and how it affects the design of the receptacle in which it's going to be made. Then I'm going to talk about how you actually make the stuff, which is actually a little bit more subtle than you might think. And then, of course, in tribute to our green fraternity, I shall discourse on recycling. So, what is it? Most of us have seen it, and we think about two pieces of paper with a wiggly bit in the middle. But in fact, formally, it's a three-ply structure with two outer liners, as they're known, joined together by the middle layer with the sinusoidal flute structure. And bonding is made by the starch-based adhesive. The fiber, of course, comes from trees. The starches can be potato, wheat, maize, or other. So it is actually a truly renewable commodity. And the initial bonding in making the flat board from which the box is subsequently produced is ingenious in the fact it can make an instantaneous bond under heat and pressure, which is actually quite a difficult thing to do with a relatively dilute, low solids, water-based adhesive, let alone one made from natural products. And if, as you see in the little picture in the bottom right hand of the screen, you strip away one of the liners, you can see the flute sitting underneath. And you'll notice that at the tips of the flutes, there's residual fiber, which has been stripped away from the liner as you peeled it off. And that's a good sign, because it means that you have a strong bond, which is actually stronger than the internal ply bond of the sheet. Now, you can make board in various weights and thicknesses. And the board is a large flat sheet, which can then be die cut to provide the blank from which we then make our three-dimensional box. It combines strength with lightness, and above all, that property makes modern distribution systems possible. Without our humble brown box, our consumer society, to a large extent, could not function. So where do we get the fiber from? Well, ultimately, it comes from trees. And we use actually two types of fiber. One for making the fluting medium is a short fiber, such as, for example, birch. And the other is the long fiber that comes from softwoods. And the production of the fiber involves the separation of the fiber, the cellulose strands, if you will, from the lignin, which is the brown binding polymer from which these things are made. And one can draw an analogy with polyester reinforced glass fiber composite, because the lignin is nature's polyester. In fact, it's strictly speaking, it's a polyphenol. The fluting medium has to have compressive strength. If you can imagine, you're trying to squash the box when you stack it. In the direction of the flute, you have to have the maximum compressive strength possible without bending. And that's why we elect to use a hardwood fiber if we're actually making the thing from virgin fiber to begin with. And the hardwoods themselves vary according to which part of the world we're dealing with, but often, for example, in Scandinavia, it will be birch. And if you've ever been to Finland, there are birch trees all over the place. This is pulped by a combination of chemistry and brute mechanical force. We pre-treat the chips made from the tree with a chemical liquor containing sulfur dioxide, which depolymerizes the lignin and enables us to free the fiber from the lignin in a device called the refiner, which is a bit like an old-fashioned millstone, except the discs are orientated in the vertical plane. They have bars between them. They rotate, or one disc rotates at high speed. And as it does so, it brushes and defibrillates the chips and frees the fiber from the lignin. And that's known as a neutral sulfite semi-chemical process, or NSSC to aficionados of the sport of corrugated containers. Now, the linerboard is made by what's known as the Kraft process. And Kraft is simply the German for strength. And I have somewhere an example of a virgin Kraft liner. This is made from a softwood, and this is pretty hefty stuff. It weighs in at 200 grams to the square meter. So this is the paper equivalent of armor plate. But something of this weight is relatively rare these days. Most liners will be about 120 to 140, perhaps even less grams per square meter. And that's made by a wholly chemical process in which we strip out and depolymerize the lignin using a hideous mixture of caustic alkali and sulfur. And that dissolves the lignin as what's known as black liquor. And interestingly, the black liquor can be burnt in the pulp mill like fuel oil. So pulp mills making Kraft products are actually self-sufficient in energy because they can use the lignin to power themselves. And that gives us a brown fiber, which can also be bleached. So you can have a white liner as well as a brown one. And the white liner becomes important when we're making a highly printed product such as this, because the importance of printing and decoration in the last 40 years has increased greatly with the advent of point-of-sale displays in supermarkets, DIY stores, and so on. So the linerboard on the outside isn't simply a component of the packaging, it's also a means of conveying the manufacturer's message to the consumer. Now, the virgin Kraft has quite long fiber, 3.3 millimeters. And fiber length is important to us because the longer the fiber in any paper, the greater the number of crossover points and therefore bonds between fibers can be made. And that's important. If we think about, say, the Forth Bridge, the more rivets you have joining to the girders together, the stronger the bridge will be. The fact which Sir Thomas Booch overlooked when he built the first Tay Bridge with catastrophic results. So with paper, the longer the fiber, the greater the tensile and burst strength. We will get there eventually. Come on, guys. There we are. Now, most of us in this country don't have the luxury of virgin corrugated containers. Most of our corrugated material is made from recycled fibre. And that is, as a fibre source, much shorter than the virgin fibres, particularly the kraft. Shorter fibres do have their virtues. They give better compressive strength. And in making recycled fibre products, we also add starch to compensate for any strength loss that may be exhibited due to the recycling process. Now, all corrugated containers are not made equal. There are various types of flute defined by the frequency of the peaks of the fluting and its spacing and its thickness. So you have A flute, which is largely obsolete, C flute, which is C for coarse or cushioning, and the most common of all is B flute. We also have E flute, and this is an example of an E fluted product, and this is used in substitution for solid folding board in consumer packs such as this cat food box. And then we have micro flute, F and N, and these have been developed to improve, by and large, print quality, again in substitution for solid board products. They also enable more accurate folding, so you get a much sharper and better defined consumer pack. Now, distribution containers like this, in which came my laundry, have to be highly decorated. And I'll talk about the printing processes a little later. This slide, which I've taken from the website of an outfit called Netpack Inc., which is well worth perusing, shows you the different flute types. So we have the common B flute at the top, the much bulkier C flute in the middle, then we have the F flute, which is a micro flute, and then we have the N flute right at the bottom. And I've even seen business cards made out of N flute, because its supreme benefit is that it's extremely stiff in proportion to the weight of fibre that's involved. In the table, there are the dimensions of the flute, and we can see that the height of the flute can range from 4.7 in the original A flute down to 0.5 millimetre in the N flute. And as the height of the flutes goes down, the frequency of the flutes increases from, say, 128 in C flute down to 557 in N flute. And the flute spacing also reduces. In fact, we can plot a graph of flute height versus flute frequency, and we can see that there's an exponential relationship between the thickness of the flute and the number of flutes per unit length, which means that the larger flutes, B, C, and A, which are often used for the outer container in packaging, have good compressive strength, but the micro flute in particular, because of the higher frequency of the flutes, has much better print quality. How big is this market? Well, the output of corrugated board in this country has been estimated at 4.5 billion square meters, or 4,500 million square meters. That's an awful lot of surface. It accounts for about 2.5 million tons of product annually, and it's worth somewhat over now 2.3 billion. And of course, with the advent of home deliveries and ordering online, the amount of corrugated packaging that's being used has probably increased way beyond the 2017 figure. And corrugated itself forms 30% of all of the packaging market. So it is of considerable economic importance. So let's look a bit more about the properties and indeed the origin of corrugated board. It was first patented in England in 1856 as a liner for tall hats. And if you've seen pictures of Mr. Brunel or Mr. Lincoln, you realize they needed all the help they could get. The only virtue of tall hats, it gave you an ideal place to put your sandwiches. Corrugated board was really only used as a cushioning material until about 1871. For example, it was used in the United States for wrapping fragile items, e.g. bottles such as pharmaceutical preparations, sauces, and so on. And there is on Google a web page called History of Cardboard, which is incorrect. It should be History of Corrugated Board, but it's still worth looking at. Things started to take off in the 1880s when a gentleman called Robert H. Thompson patented machinery to produce corrugated board on a continuous basis. And he is hailed, certainly in North America, as the grandfather of the corrugated industry. What drove the development and expansion in corrugated production was the growth in demand for consumer packaging. As people began to buy more foodstuffs, which required a rigid container about them, as they began to buy more stuff in the modern sense for the home, so the demand for cheaper and lighter packaging increased. And there was also an accompanying evolution in transport modes from the railways or railroads to road transport and ultimately to air transport. Now, if you're sending things by air, the weight of the package itself, never mind the contents, becomes a very significant economic concern. Because if you simply packed your goods in wooden boxes, as I'll shortly show, the aircraft would never get off the apron. There was also a shift in the performance criteria by which corrugated containers were sold. In the beginning, in America, they had this thing called Rule 41, which was enacted by the Association of Railroad Companies over there. And there were analogous rules in this country, which decreed that the container must above all have side impact strength. And this, I think, tells us about how they loaded containers into boxcar with the Mark I boot. So if you want to protect your china, you had to make the box very strong indeed, and hence the heavyweight craft liner that I showed you earlier. As the technology of distribution changed, the emphasis came from side compressive strength to vertical in plane compressive strength because boxes were stacked, and eventually they were stacked on pallets. And if you're stacking 6 or 7 boxes on a pallet, the last thing you want is for the boxes at the bottom of the piles to give way, because then you get stacked lean, the thing flops over, the porcelain or whatever that you packed in the boxes gets smashed, and there's a hefty insurance claim. Result, genuine and widespread dissatisfaction. So the criteria, the test methods we use to evaluate corrugated have changed over the years. And lastly, in the last few decades of the 20th century, we had, as I said, the rise of the highly colored, highly decorated point of sale displays to emphasize customer appeal. And that's coincidental with the rise of self-service stores. I can remember the days when one accompanied Mama into a store, she toddled up to a lady behind a counter and recited what she wanted, and it was handed over. Now you go into a store, there isn't another soul apart from other customers to be seen. which is tough if you can't find things. Sainsbury's, are you listening? Now, I am old enough to remember when we had these wonderful things, fruit crates. And these were inordinately useful to an inventive child because you could stick wheels on them and make go-karts. You could adapt them to make impromptu furniture, or even separate out the planks and use them as a basis for model boats if you were so inclined. About 1963-64, the availability of these things started to decline, much to my disgust as a child, and corrugated containers supplanted them. And it's not difficult to see why. The corrugated container has a much higher strength to weight ratio. The cost of transport is therefore lower, and it is more efficient in its use of the primary raw material, the wood fibre. Okay, how do we make these wondrous artifacts? It is in fact a very ingenious process, because if you ever stuck bits of paper or card together with a starch-based, water-based adhesive, you realize to get it to stick very quickly is next to impossible. Although it's better than super glue, which doesn't stick at all except your fingers. So the raw materials from which we make these structures, fluting medium, certainly in this country, would be between 70 and 120 grams per square metre. GSM, grams per square metre, is the lingua franca of the modern paper industry for determining the weight of the product. Liner boards can be virgin kraft or recycled, and they generally are in the range 108 to 120, although for some specialized applications, you can go up, as I've showed you, to maybe 200 GSM. But of course, the limitation on that is cost. You can get uncoated, unbleached, the traditional brown liner. You can get the white top liner where you have bleached fiber on the outer layer. And the liner itself can be composed of multiple layers. So you can have a white outer layer, a recycled fiber inner layer, and a recycled fiber middle layer, and a virgin kraft inner layer. You can also get coated liners, and in fact, the sample here, both of the lawnmower and the cat fuel, cats love this stuff, is in fact a coated product. It's clay coated. It's like a high quality, what the Americans call art paper that you find in glossy magazines or in good quality books of railway photographs, because the flat, smooth surface improves the definition of the print. How do we make the stuff? Whoops, solo. Well, first of all, you have to define the properties of the raw material you're starting with. And you're preoccupied with the compressive strength in the plane of the sheet. So we can use the short span compression test, particularly for the fluting medium. So you take a 50mm wide strip and you anchor it very closely between the jaws of the testing apparatus. You apply a force and measure the point at which it yields. In the ring crush next to it, you have two discs, each with an annular groove. You wind your sample into a ring, you put it in the between the two discs, apply a force, and again, it's the force until the thing gives way. You can measure tensile strength, which is important not only to the properties of the final product, but also to the production process. You can apply flat crush, where you squeeze the flutes to see how resistant they are to sideways force on the box. You can also flip that over and measure the compressive strength in the plane of the flutes, which is very important to stacking strength in the containers. And then you also have a burst test, where you effectively, through air pressure, force a rubber diaphragm through the sample and measure the force necessary to achieve penetration. There are also various tests for absorbency, which is important to both the gluing and the printing of the board. So there are two main stages in producing a flat board to begin with. The first is what we call single-face board. And that's just a strip of liner, which is glued to one side of the actual fluted product in the middle. And that requires quite a bit of preparation in terms of heat and moisture, both for the formation of the flutes out of a flat sheet that's going into the machine, but also for the gluability of the fluting to the liner. Because what we want to achieve, as I'll show in a little while, is very quickly a viscoelastic grab between the tip of the fluting and the liner, normally the inner liner of the final box. Then there comes a double backer, where you add the second liner, and this is normally the outer liner, with an exception I'll deal with later. And there again, you're applying glue to the tips of the fluting medium, but this time anchored in the single-face board. You then bring up the liner, give it a gentle squeeze rather than the almighty thump you do in the single-facing process. You cure the adhesive, and then you can chop a continuous length of board into either individual boards, which will then go on to be made up into boxes, or there and then you can use a thing called a rotary die cutter to punch out a blank. And in fact, if you open out a box, this is the blank, and this would have been made in line at the double backer. You chop out the interstices between the flaps, and you crease the thing so that it can be easily and neatly folded up and glued together. And this is what single-face board looks like. It's actually quite wiggly in the long direction of the strip, but in the direction of the fluting, even at this stage, it's quite strong. So you can imagine why the Americans were keen on wrapping this stuff around glass bottles to protect them in transit, because the fluting gives a necessary degree of cushioning. So the corrugator itself has a number of components. You've got at one end the single facer, where we're making our rather wiggly single face board. And then at the other end, you've got the double backer, where we're combining it with the second or outer liner, applying glue, pushing the two together, and heating them on an extended hot plate, literally a polished steel plate with either steam boxes or infrared heating underneath. You may then die cut it to provide the blank I talked about earlier, chop it off into discrete sheets and stack it. Now there's a further stage I haven't shown on the diagram, in that when you get the board or the blanks off the end of the corrugator, you put them in a room with a conditioned environment, because we're putting water into the sheet during the gluing process. And if we don't allow that water to equilibrate, we will have curl. And if you have a box blank which is curly, there is no way easily on a modern packaging line you can make it up into the final container. So in the single face process, we have two unwinds. These contains great reels of paper, one of fluting, the other of the inner liner. And the fluting goes through a tortuous path over heating cylinders to raise its temperature and rollers to control the tension in the system. It then hits the first of the corrugator rolls. Now the corrugator rolls are steel rolls with the flute profile machined longitudinally on their surface. And the profile of the fluting medium, as we call it, derives from the profile of the flutes that have been milled into the surface of the steel rolls. These are heated, and they're actually quite hot. They're 175 degrees C as an average operating temperature. And the heat and the moisture which you've applied in a steam shower beforehand enable you to distort the sheet of board out of its plane to form our sinusoidal characteristic fluting. That is then carried around on the second fluting roll and brought up against the liner, which itself will have been preconditioned with heat and moisture. And on the way there, the flute tips pick up starch from an applicator. Originally, this was a roll coat, and now they use a modern slip coater. And there is an almighty thump as the two are brought together. And that thump, as I'll show you, is essential to the formation of the initial glue bond. Because if things, whoa, hello. Somebody put a coin in the meter, will you? It's really coming. It's important that we make a viscoelastic bond between the fluting and the liner at this point, because if we fail to do that and the two fall apart, the whole of the process is dead in the water. Assuming we are successful, the single face board is carried over to the bridge, and the bridge is simply a conveyor that connects the two halves of the corrugator. It has another function, as I've indicated here, that it can hold festoons of the board to encourage the curing of the adhesive and improve the strength for the next stage. Excuse me while I adjust my moisture content. Now, this is a simple single facer, which is made by a company in Amritsar in India. And I've included it because it provides an illustration of the real unwind for the fluting medium and the liner, the glue applicator roll, the preconditions and the corrugator roll, which are in this unit here. So it's a modular construction. And then in this particular one, we have a rotary guillotine or die cutter to chop the board from a continuous strip into discrete sheets. And it's typical of the simpler type of product, which gives good service in developing countries, catering for local markets. I haven't shown you very many pictures of a modern single facer. This one's a picture of a BHS single facer from Germany. And to my mind, it looks like a supercomputer. You can't see a darn thing of its workings. There is a good reason for this, and that is that A, a modern high-speed corrugator is noisy. Two, you need to control the atmosphere, around the single facer in particular to avoid curl due to moisture imbalance. And it's also to stop people sticking their fingers into the workings, because corrugated fingers ain't no fun. And single facer types, there are various proprietary configurations. Some have a cassette construction so that, for example, you can pull out individual components from servicing, like the glue roll or the corrugator roll or the preconditioner. Some are modular, so as I've shown with the Indian corrugator, you have discrete units that can be literally bolted together to give the combination of processes you require. And you also have different systems for controlling the fluting medium as it's going into the knit between the corrugator rolls themselves. And often it will be held in place by air pressure applied through a plenum. Now, modern corrugating plant does not hang around. The production speeds can be up to somewhere between 200 and 500 meters a minute, depending on the nature of the product. Widths can be up to 3.35 meters, which in old money is something like 11 foot. And that width puts a lot of engineering expertise at a premium in terms of ensuring the rigidity of the rollers, that they don't sag, and also making sure that the bearings don't give way at the speeds we're operating at. And at 500 meters a minute for a high-end unit at that sort of width, we're churning out 1,650 meters of board per minute. And if something goes wrong that impairs the quality, that's an awful lot of duff product awful quick. Let's consider the engineering of the actual preconditioning process, because if you don't precondition the fluting, then you get various defects. You can get high-lows, which are variations in the fluting height, which means that some of the flutes get stuck and others don't. You can also get, in extreme cases, particularly with virgin fluting, the flute is actually broken. It's snapped in two under the force of the corrugator rolls. So we might have 112 GSM fluting medium preheated to 80 grams. It requires 2,800 joules per square meter in the form of a steam shower generally to raise the temperature to 97 degrees C, and the moisture content from 7.8 to 9%. And the heat and the moisture control are essential not only to flute formation, to plasticize the medium, but also to the bonding process itself. And these figures were put together by a former colleague of mine from Bowwaters, he was, called Peter Hyten, in a paper in the American magazine in 1993. Now, again, this is just a quick look at the single facer, because what we're aiming for is something which is stuck together sufficiently well that we can then take it to the next stage of the proceeding. But it's worth stopping and considering actually how extreme the conditions are in the single facer. The pressure in the nip between the second corrugator roll and the liner is about 340 to 580 kilograms per centimeter, kilograms force, which is why modern corrugators are heavily enclosed, because there is no way your fingers would survive passage through the nip. The pressure is essential to develop the green bond, to actually shear down the components of the starch adhesive and make them stick. The corrugator linear speed is 4 meters per second. But when you're forming the fluting from the fluting medium, you're actually pushing some of the paper out of the plane of the sheet. So effectively, in terms of its in-plane length, you're shortening the thing. If you take, I don't have a sample here, but if you take some corrugated medium that actually has been made into a corrugated form and stretch it out, it comes out about a third longer than the corrugated product itself. And this is known as take-up. And so the take-up ratio and the output side is, if that's 4 meters per second, the take-up ratio is 1.33 meters per second, and the speed going into the nip is 5.3. So the bit of the single facer concerned with delivering from the unwind to the fluting roll is actually running faster than the rest of the single facer. But most crucially, we should look at the dwell times in this thing. If you look at it in milliseconds, at 4 meters per second, the dwell time between, 4 meters a second, the dwell time between the fluting rolls is 6 milliseconds. Before the glue roll, where the glue is applied to the flute tips, 1.5. Glue application contact time, 3 milliseconds. And before the pressure roll, where we're forcing the fluting against the inner liner, 60 milliseconds. And the contact time with the liner as it goes through the pressure roll, in other words, the pressure pulse duration, is 1.15 milliseconds. So you've only got 2 milliseconds to persuade a relatively runny starch-based adhesive to make a bond that's strong enough to hold the board together through the rest of the manufacturing process. How do we do this? Well, originally they used sodium silicate solution, best known as water glass, but they soon found that at any speed, the innards of the single face had got coated with something resembling granite, which meant that you could only clean the thing down with having a cold chisel. So this dropped out of fashion, and instead starch-based adhesives came in. But the problem is how to achieve relatively high solids, low viscosity, and high tech in a millisecond time step. The answer came in the form of a thing called the Stein-Hall formulation, which sounds like the title of a detective thriller or spy thriller. It's actually deceptively simple. You have a carrier phase made of totally dissolved starch, which is a bit like wallpaper glue. And into that you disperse some pre-swollen starch granules. If you apply heat and moisture to starch, it will swell. And the solids content in total is about 24 to 30% dry basis. The addition level to the flute tips over the board is about 4 to 6 grams per square meter. So you're not putting an awful lot on. And that's popular with the corrugator operators because, of course, the further you can make the glue go, the cheaper it is. And the carrier phase provides not only a transport medium to suspend the starch granules, but also a water source for rapid granule swelling under the heat and pressure of the corrugator nib. I won't go into this in great detail, but in the carrier phase, you make it up out of starch, water, and some caustic soda and alkali to completely disperse the starch. And you mix that to a suspension of raw starch in water. You also, at one time, used to add borax, and the borax acts as a cross-linking agent to improve the adhesive strength. Because of environmental considerations in recycling, borax is not as popular as it used to be, and various synthetic additives may be put in. Now, the glue itself is only one component of the gluing process. The other is the paper. And we're concerned with things like surface roughness and paper porosity, which sometimes are together known as the rugosity of the paper. Fibre absorbency is important because that governs the rapid take-up of moisture from the adhesive as it's setting. Compressibility and conformability of the paper are important through its thickness, what we call the Z direction, because that governs A, the amount of pressure that can be transmitted to the glue bond, and B, the actual area of the glue bond itself between the curved flute tip and the interior surface of the liner. And then finally, there's moisture content, not only because of its possible retarding effect on the glue cure, but also because paradoxically, the more moist the paper is within certain limits, the better the heat transfer. And more heat equals more rapid cure. And variation in these paper properties causes problems in glue bond formation in both the machine and the cross direction. And therefore, ultimately, variations in the compressive strength and performance of the case. You can also get defects arising from the gluing process itself, displacement onto the flanks of the flute. So there's actually a very limited contact area for the glue to operate on. That suggests that the glue is perhaps not of sufficiently high viscosity. You get this problem of brittle bonding, and that's when you've got too much heat going into the system and the glue is cooked off even before it hits the liner board that's coming in to meet it. The solution to that is quite simple. You increase the speed of the corrugator. That reduces the dwell time for heat input from the preconditioners and the heating rolls, and therefore it restricts the amount of swelling of the starch granules before they're rammed up against the liner. And you've also got lateral non-uniformity in the amount of glue added arising from perhaps mechanical defects in the glue applicator system. So again, this is what we get when we've single-faced the board. We get the liner on one side and the fluting on the other, ready for the next stage. Now, this is a double backer. Again, we have application of the starch to the surface of the flute tips on the single-face board, combination with usually the outer liner, and contact with the hot plate to cure the glue. The important difference between the double backer and the single facer, well, there are two. One is we're not making flutes, they're made already. The second is because the flutes are there, we can't apply a lot of pressure to get the glue to set. More pressure means more granule rupture and better heat transfer. So we swap pressure for contact time, and we have an extended contact over the hot plate, sufficient to cure the adhesive to the point where, in fact, we can die cut it or simply chop it into boards and continue on to the next stage. And so the strength properties of board we produce are, the in-plane compressive strength, which is hugely important to the end performance of the case, particularly in transportation. The side impact resistance and the torsional bending stiffness of the board, so it doesn't twist. The finishing means cutting into sheets or die cutting into container blanks, which I've talked about before, and that is accompanied by, or sometimes followed by, creasing to create the corners of the container, folding, and then gluing at what is grandly known as the manufacturer's joint, which is this tab to this face of the container. And lo and behold, you have a box. And the folding and gluing operation may be done by the end user or in what is known as a merchant board plant, where they buy in flat board and then develop that to produce a final box. And in that process, they may also print the board as well. And this is an example of rotary die cutting that cuts out the box blank. And this can take place either at the end of the corrugator or as a separate process. And essentially, you have a cylinder with various sharp edges incorporated into it, or blunt ones where you want simply to create a fold or crease in the board. And as that rotates, it comes in contact with the board and punches out the blank. And that's the example of the thing I've showed you here of the die cut blank. It's flat until you start to erect the card. Well, I said before, you can have gluing problems related to the rate of cure and the bonding uniformity of the glue at the flute tips. You can have board warp and curls, and that relates to how you treat the sheet once it comes off the corrugator. You have to control the equilibration of moisture within the board, otherwise, being made from paper, it will curl. And then we've got washboarding. And this, as we see in the picture, is the sagging of the inner or the outer liner between the flutes. So most corrugated containers have that to a limited extent. Now, you can tolerate a little bit on the inside because nobody's going to look at the inside of a corrugated container. It is no good if you're printing on it, though, because there may be areas in the wells or recesses between the flutes which don't pick up the printing ink, and you get a lousy image. And for that reason, amongst others, the outer liner is normally of heavier weight and of smoother surface than the inner one. So we want to make a nice printed image of our pussycat having his lunch. Well, we've got a number of means of doing that, both of actually in terms of the printing process and in terms of how it's applied to the container. We have flexography. And this is the transfer of a water-based, normally acrylic ink, from a polymeric plate, so-called, which is actually a flexible polymeric sheet round a printing cylinder, and the image area is defined by high spots on the plate. You can either have solid color, as print on here, which is one color splodged on like a rubber stamp, or you can have full-blown what's known as process color, where the image is built up of individual dots. And I'll explain a little more about that in a minute. Next comes lithography. And this is a metal plate process where the image area is defined not by the relief of the features on the surface, but by changes in surface chemistry from oleophilic, oil-loving areas that accept the ink. And these in turn are defined by hydrophilic or water-loving areas that define the non-image areas round about. And that is normally a 4-color or 5-color printing process, halftones again, made up of dots, and at least 4 colors, cyan, yellow, magenta, and black, to which often a couple of other specialty colors are added. You can also print on, as a continuous film, an overprint varnish to protect the print quality from scuffs during the handling of the container. And also we've seen the advent of digital, inkjet, and indeed electrophotographic laser printing. And these are often used for prototyping. So you have a fancy design commissioned for your container, for your scent or your whiskey or what have you. And before committing himself, the packaging buyer will want to see a representation of the final product. And these can often conveniently be made using inkjet or laser printer on board to create the prototype, as it were. This is an example of a half-tone print. In fact, it's taken under a microscope from an area on this cat food pack. And we can see here we've got big red dots with blue dots inserted into them. And here we have blue dots, and between them is the white of the coated board beneath. And by varying the size of the dots, we can vary the intensity of the color. So you can have either almost solid dark blue or a lighter shade, because the eye doesn't resolve the dots, it just sees a continuous film. And as you see on the left here, we can overprint red dots with blue dots to create a different shade, a purple shade in this case. Printing applications. How do we incorporate a printed image into the container? Well, some of it is done by post-print. You have your corrugated board and you put it as a flat unit into usually a flexographic press, which, as I've said, can be single, or it can be a full-on multicolour print job. You can have pre-print laminates, where you take the flat board and you laminate the printed image on the sheet of paper on top. And that can often be used for high-end printed products, for high-value applications. And it can use lithography, as I've mentioned before, or it can even use gravure, which is the intaglio process used for printing banknotes and very posh magazines. You can have pre-print outer liners. And these are the outer liner, usually clay-coated, which has been printed before it's fed into the corrugator. Now, you've got a fancy and expensive print job. The last thing you want to do is drag it over those hot plates on the double backer. So what you do is you apply this actually in the single facer because it's a gentler path as far as the outer liner goes. And as I said, for short runs, for prototyping, niche products, you can also use digital inkjet or electrophotographic system. Okay, we've made a box. How do we qualify it as being suitable for the end use? Well, you can apply a box compression test. You take the box, you put it between two platens, and you squash it and you record the amount of force necessary before it buckles, it gives way. There's a snag with this. On the one hand, it's nice and neat. You can relate the box compression test results to things like the ring crush values of the liner and the fluting. But the compression strength of a box is also strongly influenced by its content. If you have a box full of soup tins, right up to the top of the box, it's going to be a lot more resistant to compression than if you have a box full of crisp packets. And so the modern tendency is to test boxes with their intended contents in place. Now, a further factor is that the box just doesn't sit in a warehouse all its life. It's jiggled around as it's transported by road or rail or air. And so modern test methods use a vibration table on which your boxes sit to reproduce the vibrations that the box is going to experience during its transport journey. And this even goes to the extent of them fitting up trucks with load cells and transducers, feeding the results into a data gatherer, and actually getting a complete readout of all the vibrations during the course of that particular journey. And that they then feed back into the vibration table, so you get an exact simulacrum of the situation the box is going to face. And that's extremely important if you're dealing with high volumes and high value contents. We also test the box under different levels of humidity, because it must be said the weakness of any paper-based structure is its response to changes in its moisture content. And the real killer is where you're shipping in some parts of the world where you have a sharp change between climatic conditions during the day where it's hot and dry and climatic conditions during the night when it's cold and wet. So if you're going to ship from Southeast Asia to Europe, you're going to get a big variation in climatic conditions and a big variations in moisture levels inside the container. So we can take our fancy vibration table and actually put a big chamber around it and let the box experience the sorts of variations of moisture and temperature that it will experience in end use. And the final trick in box testing is to actually palletize them, because most of these containers, actually, particularly for consumer products, will be stacked on a pallet and possibly shrouded in cling film. And when you get a palletized load, it behaves as a unitary entity, and the bottom may wiggle at a different rate from the top. And so if you wish to understand thoroughly whether the box design is going to be up to the required standard, you actually have to reproduce this level of detail in the final testing. And what we're interested in is stackability, the stacking strength, and to a degree inside impact, which can arise not only from external forces, but also from the actual movement of the contents within the box under vibration. And what tends to happen if you squash a box, you get this characteristic panel failure, where these panels are pushed out at the side, the top bends towards the middle, and the corners, which are the strongest, are the last to fail. Now, it may be that the contents, for example, soup cans or automotive parts, can survive that level of deformation of the container. But if that's a container at the bottom of a stack of half a dozen boxes or more on a pallet, which is vibrating, and that box gives way, the whole of the stack can collapse sideways with consequential loss. So there's a lot more technology goes into our brown box than really we might imagine, both in production, in design, and in testing. And when it's all done and dusted, and the box is consigned, we hope, to the recycling bin, it can go around again. And this is one of the great strengths of corrugated board, that the recycling rate in the UK is over 80%, which is by far the highest of any packaging material. On average, corrugated boxes in the UK already contain 76% of recycled material, and many boxes are made from 100% recycled. The greatest technical constraint on recycling, and this is the question, how often can you recycle the fibre? How often can some long-suffering fibre go round the loop? Is that the number of cycles it can survive is limited by its length. As the fibre is recycled, so it loses a little bit of its length, it gets frayed at the edges. And loss of length means, as I said earlier, loss of bonding ability in the fibre network, and therefore loss of strength in the sheet. So once the fibre gets down to about 0.5 millimetre or less, then its days are over, and generally we're removed from the stream in the paper mill. So we take the corrugated board and we repulp it in a thing called a hydropulper, which is like a monstrous kitchen mixer, huge impeller in the bottom of a tall cylindrical tank. Once we've dispersed the fibre in water, we can then clean it using slotted screens, rotating baskets or basket screens as they're sometimes known, and centrifugal cleaners where we whiz the liquid round in a cyclone and separate it on the base of its density. And this technology comes straight from mineral processing. You will see cyclones in a recycling paper mill like David S. Smith at Kemsley. And if you are lucky enough to go around a China clay plant in Cornwall, you will see exactly the same sort of cyclones cleaning up the clay particles. We can then fractionate the fibre into short fibres for fluting and longer ones for the liner. We then form the sheet on the paper machine here, and what you're doing is squirting a long layer of the suspension of paper fibre in water. The waters drain off, the fibres bond to one another, and the rather soggy sheet at about 15 to 20% solids that is then pressed to improve its internal bond, remove further water, and then it's dried on steam heated drying cylinders. It's then wound into what we call a machine reel, which itself is slit down into smaller reels for transmission to the corrugated plant. And that's a further quality target to control the wound-in tension in the customer's reels. Because if you have variations in the tension of the unwind reels going into, say, a single facer, then if that single facer is running at, say, 450 meters a minute, that can cause all harry with the flute formation and the production of the board. To the extent you can, in the lighter weights, get the sheet to break and have to feed it up and start all over again. So wound-in tension is actually extremely important. And a good reel from a mill, you know it's good because when you hit it, it rings like a bell. I advise you to use your fist, not your head, by the way. So the conclusion of my diatribe tonight is that corrugated board combines strength with lightness, and it actually makes modern distribution systems cost effective. With solid wooden containers, air freight, for example, simply would not work. The corrugated board saves raw materials. It is made at high speed on a sophisticated piece of machinery, and yet can use a simple starch-based adhesive. The containers at the end of their life are easily recycled, and the number of cycles is limited only by the fiber length. So I hope I've lifted the lid on some of the technology that goes behind a seldom considered part of modern life. So thank you for your attention. Here are my two assistants. And if you want to actually see corrugating and paper making in action, I recommend this YouTube video, which Philip unearthed. And although it's made in America and has one or two things we wouldn't see in this country, it nonetheless gives an excellent impression of the whole process. Thank you very much.
Right, we've got plenty of time for questions. For those of you here in the think tank theatre, there are a couple of roving microphones that will shortly be starting their roaming. Please raise your hand or otherwise attract attention, and a microphone will come. I do encourage you to wait till you get the microphone, because otherwise we can probably hear you here, but people at home on Zoom won't be able to hear. Yeah. If you are at home and have a question or comment, we encourage you to use the chat function on Zoom. It's normally a little button towards the bottom of the screen, which will bring up a dialog box, and you can type a sentence or two in there. And if we spot something coming in, we'll read it out. And okay, first question.
I've been stopped waiting tonight. And this is a box of board from the show back in. What type is that? What is that? Not corrugated.
The gentleman has asked what type of box it is from the point of view of the corrugated. So I'll have a look at it.
I think it's just plain card, I think.
Right.
It's plain cardboard.
Yep. This is just what we would call carton board. It's made of, it's probably a multi-layer structure, but it's made of 3 plies, which are actually stuck together on the paper machine, not in any subsequent process. The outer layer appears to be a clay-coated bleached craft board or layer. The middle layer is probably what's known as CTMP, which is chemi-thermo-mechanical pulp. It's a form of souped up newsprint, if you like, but it's bleached. And the inner layer is uncoated craft, although it has probably a release coating on it, maybe of silicone or fluoropolymer. The doctor is in and open to diagnose any board that you may place before him.
Are rejected during the recycling process because they are too long or short. What happens to them? Can they be used in, for example, paper?
As for reuse in paper, probably not, with one exception. Sometimes it is possible to use or indeed lose short fibers in the middle layer of a multiply liner board. So effectively they've been hidden away. They've been sandwiched between longer fibers on the outside. In some cases, the cellulose sludge, which is what it is, has been used variously in brick and cement production as well. Or it can actually pass to the effluent plant and be broken down by aerobic digestion, so that it's effectively reduced to its components when it was made in the tree, that is carbon dioxide and water.
Okay, and another question, what mass fraction of fibre would be typically lost through being too short when the fibre is recycled?
Well, if you talk to the people at David S. Smith at Kemsley in Kent, they will say too damn much. Because the problem is, as we've increased the level of recycling to 80% plus, we are inevitably going to increase also the amount of shorter fibre. On a good day, depending on what comes on their belt, the actual amount of usable fibre could be as high as over 90%. On a bad day, it could be considerably less than that. Because their idea of Christmas come early would be to have a belt going into the hydropulper with American virgin craft heavy-duty tri-wall corrugated, because that would give them loads of lovely long fibre, and they could go and celebrate in the pub afterwards. But on other occasions, you can get low-quality corrugated, perhaps from, shall we say, countries in the southern hemisphere, which is little better than glorified newsprint, grey mush. And that gives them a lot of problems because it skews the average fibre length that they're going to have, either as long fibre or short fibre when they fractionate. So I can't give you a direct answer. I can only give you a politician's reply, is that it depends on what the waste merchant supplies to the mill.
One up on the top there.
I'm just curious about the sort of interface between the product applications for the corrugated cardboard and board that's got a honeycomb type reinforcement. Are they very different, obviously very different manufacturing techniques, but from a use point of view, do they tend to overlap? And obviously one is more expensive than the other. Interested in your comments on the interface between the two products.
Well, I'm aware of the honeycomb board, and its main property, if it's, at least I'm assuming you've seen the same stuff as I have, is that it is resistant to sideways forces. It has great cushioning strength because you're trying to squash the honeycomb along its axis, and you're trying to squash a cylinder, in other words. So just as the corrugated board has its greatest compressive strength along the axis of the flutes, so the honeycomb board, in which the axes of the honeycombs are at right angles to the surface, will have its greatest resistance along the axis of the honeycomb. So if you belt it from the side, it has very great resistance to crushing and burst. It is bulkier than corrugated board. It is more difficult, I would suspect, to make into a container. This stuff, you can crease it and bend it. It's a lot simpler. I suspect that the fabrication of honeycomb-based packaging products is probably the most difficult and therefore the most expensive step. But I don't have a great deal of honeycomb experience to match what I've been accustomed to with corrugated.
Somebody has said, fascinating talk, thank you. How is multi-level corrugated board made?
Okay, I think what the questioner means is multi-layer corrugated. This thing is a double layer box. It has C flute on the inside and E flute on the outside. And the way they do it is they have another double backer after the first one. So you've constructed one layer of board. They then bring up another single-faced board underneath it, stick that on, and that will then give you double wall. And you can actually stick on another layer of single-faced board to give you tri-wall. And these can have different fluting profiles. And it's likely that the single flute layers that you're going to incorporate in the final product may be made in a separate run on the same machine, or more likely on a separate single facer with a different flute profile. If you want to bring the changes on the flute profile, you can certainly go up to tri-wall, and that is a commercial product. And it is used for high-end application of particularly of very heavy articles like machine parts, for example. I might add that the corrugator that makes tri-wall is very long.
Thank you. In the process of answering that question, I think it's also answered the next question which is on the screen. So I think we can leave that on low. Yeah.
I'll be putting that to recycle tonight because the results come down. And now the containers put them in. They keep forming all mixture of recycle board to do with paper. They come with cardboard and cardboard like that, something like that. Or they all look like stuff away. All that. What happens when it's mixed to cardboard? What happens when they do actually get it to recycle?
Well, the answer is it's repulped, it's cleaned, and it's fractionated. So the fibre in the outer layers of your carton would go to make the liners, and the CTMP, the bleached mechanical pulp on the inner layer, would go in with the fluting.
So in other words, they don't have to separate the thing. They'll be able to do that.
No, they don't actually have to separate it as such. They just chuck the whole thing into the hydropulper along with everything else they've got on the belt, and they separate the fibre once it has been dispersed in water.
All right, because we put newspapers, we put magazines.
Yes. The problem with newspaper is the ash content, the mineral content, which isn't really reusable, and the shortness of the fibre, because newsprint in this country is itself recycled, so you're recycling something that's been recycled already. What paper makers would love is virgin newsprint with, say, 10% of craft fibre in it, because that will give them the much desired fibrillate that they need.
Okay. Thank you.
Not a question, just a comment. There is another use for the tall hats in Victorian time. Chaps who were getting on and had prostatic hypertrophy would keep their catheter in their top.
Right. Well, thank you for medical. I thought you were going to tell me that certain gentlemen found them useful if they cited a member of the opposite sex. But we won't go any further.
I think maybe we should draw things to a close at this time before the conversation gets any worse. Once again, thank you, Nigel, for a very, very interesting and informative talk. I think we've all learned a great deal about a subject which doesn't usually get a great deal of attention. So let's just express our thanks in the normal way. As I said, this is the last meeting of Newcombe Midlands for the season. We will be reconvening in October when find the right bit of paper, when David Hardwick will be talking on Wednesday, the 5th of October, here at 7 p.m, about the Newcomen Engine House at Brislington, that's near Bristol. And he'll be discussing the historical and archaeological appraisal of the standing building in Brislington. So put that in your diaries. We've been quite successful with our hybrid meetings so far, so I suspect that all being well, we should be able to still do hybrid meetings, whether or not the health situation demands it or not. And so yeah, have a good summer. Come back in October. We will probably have our branch AGM that evening briefly, 5 or 10 minute meeting, just to let you know. And meanwhile, let's hope we're back to normal health-wise by that time.
Can I just pass in slightly?
Yep.
There is a provisional programme for next winter, and there are copies here. There are 2 lectures still to be settled, but the other 5, including Brislington, are already on the list. So do take ones of those if you feel you can use them as a reminder or display them somewhere.
And for those of you listening at home, have a look on the Newcomen website, and details will appear in due course. So have a good summer. One more announcement.
Yeah, there is also a flyer here for a lecture I'm giving in this building on the 21st of April, 7 o'clock in the evening. That will be in the planetarium.
Oh, no.
Again, on this level in the building. I don't know how on earth you reach it. I'm giving a lecture, but I haven't actually met it at night. So no doubt arrangements will be made to get people into that. And I'm talking about the Smithwick engine, the big engine downstairs, the Vulcan one. The world's oldest working steam engine. So it's that.
And again, I suspect there'll be details on a website probably. But certainly the think tank website will have mention of that. So thank you very much. Thanks to those who've been here, and thank you for those of you at home.